By the way, so correction regarding with the one that I posted in our Facebook group. So I put there module 2. Okay. So again, correction. So should be module 1, part 2. Okay, not module 2. Okay. So in module 1, there's 3 parts. Okay. So I separated those or that module into 3. Okay. Since there's too many slides. So I separated that one into 3. Okay, so this is the part 2 already, and the next meeting will be the part 3. Okay, so last 1 minute for the others. So how many are we now? 17, 18. So how many are we last meeting? Can you guys recall?
I think 23, sir.
23. All right, so I'm not really expecting to have the same count of participants since, there's a lot of circumstances. But anyway, so let's wait 1 more minute. So 18, that's already good. Considering that there were 37, I guess, 37 or 38 students. So yeah, half of you are attending in our synchronous meeting. So that is already good to me. So before we start our discussion for today, do you guys have a question or a clarification? Or any concern?
None, sir.
All right. All right, so I guess there would be no other who's going to join us anymore. So let's now continue our discussion for the part, or start rather, since this is our first time having this part. Okay, so module 2, still the same logic and proofs, but just a continuation of the part 1 last meeting. Okay, so let's start with loss of logic. Okay, so basically this loss of logic has 1 to 25 numbers. Okay, so in last year, when I was teaching this one, I've let them memorize number 1 to number 25. But since, right now is an online distance learning, so I don't have the capability or the capacity for to monitor you guys if you really did memorize this one or not. So yeah, so this is like a free BT already. Okay, you don't need to memorize this one anymore, but just go back and then look back with these formulas. Okay, so first we have here the commutative properties. This one is very easy. Okay, so number 1, number 2. In here we have a connectives of or, and then we have here the connectives of n. So as you can see, P or Q is equal to Q or P. So meaning you can interchange those two variables. All right. So this is only applicable for or and then and connectives. All right. So this is for the or, and then this is for the and. So P and Q is equal to Q and P. All right. So that's it for commutative properties. Very easy. And the next one is associative properties, wherein if we have two distinct connectives, as you can see right here, we have or, and then and. So meaning you can interchange the bracket or the arrangement of the bracket. Okay, so it could be in Q or R or in P or Q. So the same with N. So it could be in Q and R or in P and Q. Okay, so either of those arrangement. So they are just the same. Okay, but in terms of applying associative properties. Okay, so did you guys get this one so far? 1 to 4, commutative and then associative. No problem at all.
Yes, sir. Yes, sir.
Yes, sir.
Yes, I don't need to explain this one much more since this one is super easy. And then next one is distributed properties. So this one is just the applying FOIL method. If ever you're familiar with FOIL method, first, outer, inner, and then last. So this is the same with these variables. So basically, you're just distributing this one, P, in this Q and R, okay, or in this expression, Q and R. Okay, so P times Q and R, which is this one, and then, sorry, P times Q, which is this one, and then P times R, which is this one. And then, as you can see, the one that is outside, okay, the connectives that is outside is now the one that is inside, okay? And then the one that is inside is now the one that is, outside, which is this one. Okay, so that's your pattern when it comes to applying distributed properties. Okay, so distributing this one into those two variables and then putting this one inside and then this one outside. Right? So the same with this one. So the one thing that you should know when it comes to applying distributed properties is their connectives. So they should have, or you should have, different connectives like or and end, or and or. Okay, because if those two are the same, like or and then end, then that one is not applicable in distributed properties. So you can only apply on that one is the associative properties, but not distributed. So take note, you should have this kind of setup. So or and then and or. Okay, and then so this is the equivalent. Okay, did you guys get this one so far?
Yes,
Yes,
sir.
sir.
All right. So
Sir.
again, the one that is connected that is outside is now the one that is inside, and then the one that is inside is now the one that is outside. All right. So that's it for distributed properties. And then idempotent properties. So this is common sense already, because if you're going to have, two the same variables, then whatever is the value of this one is the same with the value of this one. So we could say that P and P is equal to P. Because if this one is true, then this one is also true. If this one is false, then this one is already false. So this one is applicable in end and in or only. Okay? So P and P and then P or P would be equal to P only. And then the double negation. So this one is also super easy since you already know how to apply, or how to multiply negative. So negative times negative will become positive. Negative times positive will become negative. So in here, double negation is equal to positive. Right? So did you guys get those so far, 1 to 9?
Yes, sir.
Yes, sir.
Yes, sir.
For now, you don't need to memorize, okay,
Yes.
their name, double negation, idempotent properties, distributed properties, associative, and then commutative. So you don't need to memorize their names for now. What you need to know from what we're discussing right now is the logic on why they are equal with each other, okay, on why this left side is equal to the right side, okay. So I guess we don't have a problem on number 1 to number 9. And later on, there are some equivalence expressions wherein it has a long derivation. So that is why we won't be able to, discuss those things anymore. But they have their own derivation. That's why they've come up with that equivalence. Right. So moving on, we have here identity, wherein if we have this kind of setup P and P, this one is already equal to P. Why? Because if you're going to take a look on this one, if it's n, okay, and as we all know in n, it doesn't matter on how many true values you have. But if you have one false and then let's say 9 true, still the entire statement will become false, okay, because we're using n. But if it's or, okay, no matter how many false statement that you have in that entire statements, as long as you have one true, and then the value of that entire statement is already true. So that is why the value of this one is depending on our letter P. So we don't know if this one is true or false yet. So if this one is true, then this one is true. If this one is false, then this one is already false. So the same with or. If this one is true, then this one is already true. The same with false. Okay, if this one is false, then this one is already false. Okay, so take note, this is only applicable for false or in or, and then having a false statement, and then having a true statement. Okay, if this one is P and then false, okay, so that is a different setup, which is now the domination. Okay, so again, this one is only applicable for this kind of setup. So P and T and then P or F. But if this one is P and F, then that one is already domination. Okay, so no matter what is the value of our P, it's still the same. That one is already false, since we already know that there is one false on the entire statement. So the same with or, if we have one true value on the entire statement, then that statement or that entire statement is already true. Okay, so did you guys get this one so far? Identity and domination.
Yes, sir.
All right, so anyway, you don't really need to memorize this one. If you're going to evaluate this one, you will know the correct value. Okay, so even though you don't know what is identity and then what is domination, as long as you know you've evaluated each variable, let's say you already know the value of this one, then you will already know what is the result, even though you don't know the loss of identity or loss of domination. As long as you know the truth values of the and then the or. Okay. So moving on, we have here absorption, wherein so basically, if you're going to have a value, okay, let's say let's assume we have a true value for P. Okay, so true and true or Q. Okay, so in here, since that one is or, then the entire statement or the statement on this one, close and open parenthesis, is already true, right? So that is why true and true is already true. Okay, so as you can see, whatever is the value of our P, okay, will be our final value, okay, or will be our deciding value at the end. So if we have false value here, false and then N and then false or Q, okay, and then as you all know, in end, if there is one false on the entire statement, the entire statement is already false. Okay, so that is why we call this one absorption, because whatever is the value of P will be our final value. All right, so you should, I guess this one, you should really memorize this one right now. Okay, this is very important in let's say simplifying a certain expression. So for example, it is asking you why this one is equal to the right side. And then on the left side, you have 8 variables. And then on the right side, you only have 3 variables. So this is where this law become useful, because as you can see, from 3 variables, it became 1 variable only, right? So yeah, you should really memorize this one as early as of now. The rest, then you can just go back to them if you'll be needing them in some activities. But for this one, this is very important. Okay. So did you guys get this one so far? On why we have this expression equal to this expression? So I think Miss Peya is speaking, but I didn't hear anything. Anyway, so if you didn't get this one yet, so try putting, let's say, an assumed value. So it could be true or false, and then you will know later on why we have this result. Okay, so the same with this one. So this is only applicable for this kind of setup. So we have and then or, and then if we have two the same variables, okay, which is p outside and then the p inside of this parenthesis. Okay, so the same with this one. Even though this one is or and then this one is and, still the result is p. All right. And then for De Morgan's law, okay, so this one is like negating the entire statement. So basically, if you're going to negate this one, so of course, it's like distributed law. So one, it's like distributing this negative sign inside of the parentheses. So negative times p will become negative p or negated p, and then negative times or will become n. Okay, so again, this is only applicable for n. Okay, if you're going to negate n, if you're going to negate or, it will become n. So vice versa, if you're going to negate or, it will become n. Okay, but if you're going to negate the conditional or biconditional, then that's a different story already. Okay, so this is only applicable for conjunction and then disjunction. So in here, you're just basically distributing this negative sign. So this expression is equal to this expression. So negation p, and then from or it will become n, and then negation q. So the same with this one. So this n will become or, and then your p and q will now become negative. So did you guys get this one so far from number 10 to number 17?
Yes, sir.
Clear, sir.
Yes, sir.
Yes, sir.
Right. So on what part that you guys are having a hard time in understanding now? None so far? Absorption.
None,
None.
sir.
Is this okay to you guys? Did you guys already get this one on why we have this result?
Yes, sir.
Yes, sir.
Okay, that's good then. Okay, so the same with De Morgan's law. Okay, next we have here the P conditional Q, which is equal to not P or Q. Okay, so in here, in implication, it is not actually easy to say that this one is equal to this one because of this and that. So we have a long derivation for that one. Okay, so for number 18, 19, and then 20. Okay, so I will leave the research part unto you guys on how they come up with this expression. So for now, the only thing that I can advise to you is memorize number 18, 19, and 20, or not really memorize, familiarize. Okay, at least familiarize this one, 18, 19, and then 20. Okay, so for implication, so as you can see right here, our conditional became or. Okay, so you could say that if we have P conditional Q, just negate the hypothesis, and then your condition, statement, or connectives will become or, and then the conclusion will stay as it is. Okay, so I won't be able to explain any further because this one has a long derivation, and then if I will explain this one step by step, then it will consume maybe 10 to 20 minutes on just arriving with this result. So the same with this other example, wherein again, so this P will be negated or hypothesis will be negated, and then these connectives, conditional, will be become or, and then the conclusion will stay as it is. Okay. So if we have another example, which is not P, and then conditional Q, then that one is already P, conditional, not Q. Okay. So yeah, that's how we convert this conditional into or statement. So moving on, we have here contrapositive. So this one is quite logical, but then again, this one has a derivation on why they've come up with this kind of expression. So from P conditional Q, okay, our hypothesis became our conclusion, and then our conclusion became our hypothesis in a negated way. Okay, so if you want to convert this one into, hypothesis to conclusion, conclusion to hypothesis, you have to negate their values, just like what happened on this expression. Okay, so interchange and then negate, and then nothing will change in our connectives. Still conditional. So we call this one contrapositive. All right, so the same with this one. This number 19 and 20 are contrapositive, just an interchange format of variables. So this hypothesis will become your conclusion in negated way, and then this conclusion will become your hypothesis in negated way also. Okay. So it says here, converse is equal to inverse. So prove. So we have here the proof on why or how they are equal using a truth table. So this one, P conditional Q is equal to not Q conditional not P, which is this one. Okay, number 19. So if you're going to take a look at this one, or if you're going to evaluate ever their values, so you'll come up with those results. So true, false, true, true, and then true, false, true, true. So I will leave the analysis part with you guys once we are done with this part 2. Okay, so this will be your assignment, okay, but not recorded. Okay, just for you to know on why they are equal with each other using a truth table. Okay, so the same with this one. Q conditional P is equal to not P conditional not Q. Okay. So true, true, false, true, 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 false, true. So as you can see, we have the same value or results. All right. So again, for this one, you can memorize this one. Okay. And then if you are not convinced why we are or why this one is not equal to this one, then you can try to search on the internet on how they come up with this kind of equation. Okay. So did you guys get this one so far?
Yes, sir.
How about the others? How about you, Mr. Abdul? Abdul Wahab?
Yes, sir.
Can you follow so far?
Yes, sir.
All right.
Everything's clear.
Okay, so if you have a question, so feel free to ask me anytime, okay? All right, so moving on, we have here number 21 to 25, okay? So again, these expressions has now their own derivations on why they come up with those expressions, okay? So for example, this one, not P conditional Q is equal to P and not Q, right? So if you have this kind of setup, then we could say that this one is equivalent to this P and not Q, okay? So why? First of all, you can prove this one using a truth table. That's super easy, okay? Of course, it will come up with the same values or results. And then second, if you want to have a derivation, then you can apply the other laws of logic, okay? From number 1 to number 20, okay, the one that you've learned so far, on why or how did we guys come up with this kind of expression, okay? So for now, I won't be able to explain this one on why this one or how this one is equal to this expression, okay? Again, my only advice is for you to prove this one using a truth table or prove this one using derivation, okay? And then again, so since it's not comprehensible by using logical thinking only, so all you need to do is memorize this one. So if you have this kind of expression, then you could say that it is equal with this expression. Okay. So I recommend you guys to memorize number 21, number 22, 23, 24, 21 up to 23 only, okay? Because 24 and 25 is super easy, okay? And number 22, this one is actually quite logical, okay? But then again, it has its own derivation on how they've come up with this expression. So P by conditional Q. So meaning P must be sufficient to Q and then Q must be sufficient to Q, okay? So as you can see right here, P conditional Q and Q conditional P. So it's like, you know, having a vice versa statement. So P or your hypothesis must be sufficient to your conclusion, and then your conclusion must be sufficient to your hypothesis. Okay. So I guess we don't have a problem with this one, but on this one, so this one is equal with this one, and then this one is also equal with this one. Okay. So this one is not, again, comprehensible. Okay, it's hard to analyze on why we have this kind of expression just by looking at it. So for you to be able to solve on how they come up with this kind of expression, so you can search on the internet for derivations using conditional. So what are the equivalence expressions or formula, and also try to search on how they did come up with this with that kind of expression. So what are the steps that they've done on how they got this kind of expression? Okay, so as you can see, this p conditional q became, negated, and then this conditional became and then this and became or, and then conditional became and then their values stays the same, right? And then for number 23, so as you can see, this one is similar with number 22, but it's just that the entire statement is being negated. So if you have this kind of setup, this one is equal to px or q. Or in other words, so you can derive this one into this. So this p is actually equal to p and not q, or this q is equal to q and not p. Okay. So this one is actually quite similar with this one, like having p must be sufficient to q, q must be sufficient to q. Okay. So you're going to take a look on this one. Your hypothesis here became our conclusion, but in a negated way. And then your conclusion here became our hypothesis, but then again, it's negated. So negative times negative became positive. All right. And then for number 24, so this one is super easy. So if you have this kind of setup, p and not p, so as always, you're going to have a false value. Okay, no matter what is the value of your p, because if it's true, then it will become false. If it's false, then it will become true. Okay. And having a false on that statement or in this kind of setup will be always false. So the same with number 25. If it's or if there is one true already, then the entire statement is already true. Okay. So no matter what is the value of your letter P in here. All right. So is it difficult so far? Or easy? Or need practice? Or you could just say, sorry, we just need to familiarize the formulas or the laws of logic formulas. So is it option 1, option 2, or option number 3?
3, sir.
Number 3.
3, sir.
Who's
Option 2,
having a
sir.
hard time? All right, so who's having a hard time in understanding our laws of logic? All right, so I guess none. So at first, if you're going to take a look on this one, so yeah, there's so many formulas, but if you're going to analyze them one by one, most of them are super easy to understand. Okay, and then most of them are, doesn't really need to be memorized or doesn't really need to be analyzed, since with you guys having your previous knowledge on your math instructors or math subjects, you guys already know some of this, especially distributed, associative, and then commutative. You guys already those kind of methods. But for the others, like for example 21 and then number 22 and then 23, okay, so they've used the laws of logic, okay, this one, and then this one on how they've come up with such expressions. Okay. All right, so moving on, we have here the summaries of laws of logic, but take note some of our formulas here are not similar with what we discussed in here. Like for example, these domination, okay, in here it's domination, but in summary, we call that one annihilation. Okay, so two different names but same method. And then what else? And this one is called inverse, I guess. Yeah, inverse. Yeah, and then this one is called inverse. It's just that it's not indicated that this one is not inverse. So this one is inverse loss. Then what else? Identity. So that's already discussed. Commutative identity. And then some numbers, like for example, number 21, 22, and then number 23. So they were not included in here because the derivation from number 21 to 23 are quite long. Okay, so the one that is being summarized here are comprehensible by our logical imagination. Okay, just by looking at it, yes, you can see that this one is equal to this one. But the others, like for example, 21, 22, 23, it's not. Okay, it's kind of difficult on why they've come up with that kind of expression. So just be very on that one. Okay, this one is not complete. Right? Right, so let's have an exercise, a short exercise. Okay, so number one, using laws of logic, prove that P conditional Q is equal to not Q conditional not P. Okay, as you can see right here, this is the contrapositive a while ago, number 19. Okay, so we'll prove that using the previous knowledge that we've learned from laws of logic. Okay, so as you can see right here, we have to, we have to prove that this one is equal to this one. Okay, so the first thing that you need to do is from here, you're going to apply implication. Okay, so what is implication? It's number 18. So we have P conditional Q, it's equal to not P or Q. Okay, so that is why we have not P or Q in here. And then by using commutative or by applying commutative, we can interchange those two. Okay, so Q here became at the first part of our statement, and then our negated P here became our last statement. Okay, and then lastly, okay, we can now apply reverse implication. So why reverse implication? Because the process of implication is having a conditional into or, but if you're going to apply inverse implication, so it would be or into conditional, or from or into conditional. Okay, so that is why we call that one reverse implication. So as you can see right here, the first one was now negated, and then this or became conditional, and then the conclusion will stay as it is. Okay, so I would like you guys to take a screenshot of this one for now, for you guys to have a copy. Okay, screenshot or take a picture using your phone, so that when I'm explaining things, for example, this one, example number one, you have your own copy, so you can refer our answers on your own copy. All right, so take a picture on this one, please. So let me know once you're done in taking a picture of this one, so that we can proceed to the next one.
Done, sir.
Okay, so you can use your print screen and then paste it to Paint and then save it as JPG. Or you can use the snipping tool. Okay, just type the snipping tool and then you will have this one, and then click new, and then just grab that one, and then save that one as a JPEG. Okay, or you can just simply take a picture if you have your phone with you. Right, so I guess, or I'm hoping that all of you have already took a picture of this one so that you can have your own copy. So did you guys get this one, number one?
Yes, sir.
Yes, sir.
Yes, sir.
All right, that's good. So to those who are having a hard time in analyzing on how we've come up with this kind of solution, so you can refer to their names. So we've applied implication, so just go back to laws of logic, it's number 18, I guess, and then commutative, this one is number 2, I guess, if I'm not mistaken. And then by using reverse implication. All right. So since we now only have 1 minute and 30 seconds, so I will end our meeting for now, and then I'll just post a new link for you guys to have a part 2 of our discussion for today. Okay. So for now, I will end this one, and then just join as soon as possible. You see the link that I will post. Okay. So if ever that you have a question, so just ask it on the part 2 of our meeting later on. Okay, so goodbye for now, and then see you on part 2.